Thank you for the introduction. Hi, my name is Gohar, and I'll be talking about our project called Unleashing the Potential of Data Center SSDs by Taming Performance Variability. So let's start by looking at an interesting trend. On the x-axis, you have time, and on the y-axis, you have price in US dollars of a 1 terabyte data center grade SSD. So up until about 2024, middle of 2024, the price was roughly around 60 US dollars. Fast forward to today, it's about 4 times that, getting closer to 300 US dollars because of high demand of AI workloads which are very memory and storage intensive. So clearly SSDs and flash storage in general is a very precious and expensive commodity which is very hard to procure today. So we want to look at how is it used in data centers today, and are we making effective use of this resource? So first, you have your compute clusters in the data center, which is running your VMs, your containers, bare metal machines, and so on. And then you have a colossal number of SSDs, which is large enough that it cannot fit on a single server to meet your storage requirements. And so you connect these over high-performance networks. Now, this is pretty standard resource disaggregation. And the question we want to ask is, are we getting all the performance that we paid for? So to answer this, we ran a simple experiment on a dozen SSDs in our lab testbed. And so we have about a 90% read workload, which is, let's say, representative of what you would see in a typical data center storage cluster. And we set the latency SLO target to be about less than 1 millisecond at the tail. And the metric that we're interested in now is throughput, and so what we call IOPS, which is input-output operations in million on the y-axis. So if we go by what the vendors have advertised for these specific SSDs, we would expect an aggregate of about 5 million IOPS out of these dozen SSDs. But when we actually run this workload, we observe that we are not even able to achieve close to half of the IOPS of this total array of SSDs that we had. And that's a 50% degradation in the performance that we paid for. So the question that I want to answer today is, where did all the performance go, and are we able to achieve some of that back? So recall that we have this disaggregated storage cluster in the data center, but what existing systems do is they give equal weightage to all these SSDs when they're doing load balancing. And not only that, they treat each of the I/O requests, be it reads or writes, homogeneously across the entire fleet. Now, the point to take away is that all SSDs are actually not the same. And therefore, even a single slow SSD can limit the entire system's aggregate performance if you're not careful. So if a single SSD becomes the bottleneck, the system might start self-balancing, it might start throttling the I/O requests, and therefore, in order to meet the tail latency SLOs of the entire array, you might start observing very low throughput. So clearly, SSDs suffer from significant performance variability. But what are the sources of performance variability? And so I list 3 of these here, one of them being device heterogeneity, the other one being read-write interference, and the third one being garbage collection or other SSD-internal events that we have no control over. So ideally, we want to have policies that address each of them. So let's first look at what these sources of variability actually mean. So what is device heterogeneity? This can refer to different SSDs coming from different vendors, different models, different firmware versions, and even identical SSDs that start to behave very differently over time because of different load patterns and different wear and tear conditions. So imagine in your cluster, let's say you have half the SSDs from vendor A, the other half from vendor B. And even within these subsets, these SSDs might start looking differently over time in terms of their performance profiles. So let's quantify this a bit. So on the x-axis, you have IOPS in million, throughput, basically. On the y-axis, you have tail latency in milliseconds. And so in our testbed, we take one of these SSDs, which is shown in purple here, from vendor A, and this is able to reach about 0.35 million IOPS under the latency SLO. Another SSD, identical vendor, identical model, identical firmware, is able to only reach 0.3 million IOPS because of the different characteristics of users that the 2 SSDs went over their lifetimes. And a third SSD from a different vendor is able to reach a completely different performance profile, about 1 million IOPS under the same latency SLO. So clearly, these SSDs behave very, very differently, and overlooking this can severely hurt the performance of the array. Next, the 2 operations, reads and writes, act very differently on flash storage, and interfering them can lead to suboptimal performance. So some of the SSDs might be write optimized, which means mixing even a slight amount of reads with them can drastically hurt their performance. And the same goes for read optimized SSDs. So concretely, if you look at this performance profile. So on the x-axis, we have different read ratios. On the right extreme, you have read-only workloads. On the left extreme, you have write-only workloads. And on the y-axis, you have the throughput that you can achieve with this SSD. You'll notice that on a read-only workload, it's able to deliver about 0.75 million IOPS. And mixing only 10% reads on the left, so going to about 90% reads, or 10% writes with this, drops the throughput by about 33%. And so that's, again, a non-trivial decrease in the throughput that the SSD can achieve if you start mixing the two operations together. And finally, there's SSD-internal events that you cannot control from the software stack. So for example, garbage collection is triggered by the SSD firmware that you have no control over and can happen at any time. So most of your fleet might be operating completely normally, but a subset of them might start doing garbage collection. And what this looks like is a spike in tail latency. So on the x-axis, you have a timeline and zooming into about 1 second of time there. You'll notice that the tail latency starts to shoot up, and the SSD is actually congested during this time when it starts to do garbage collection. And there's nothing you can do from software perspective to delay this or control when it happens in most commodity SSDs. So again, if you're not careful, and if you start overloading the SSDs in these small time periods, then you can have a cascading effect of degraded performance. So all in all, we have these three sources of performance variability, and failing to cohesively manage these sources leads to this lost performance that we just saw. So why is it that existing systems are unable to meet or unable to sort of address these sources of variability? Well, first, they often have inflexible routing. So even if you're able to detect that some SSDs are slow at a moment in time, the routing policies are often such that your hands are tied, and you cannot sort of route around these SSDs, and you still continue to use these SSDs to serve your input and output requests. And number two, the sources of variability that we just saw manifest on different timescales that are often conflicting. So the SSD performance profiles differ over slower timescales as you sort of use them over time based on your usage patterns. And the load that these SSDs are sort of also observing also might differ at other timescales. Whereas events like garbage collection happen at sub-millisecond timescales, much shorter timescales than everything else. And so if a system is optimized for one of these timescales, it will completely overlook the other side and, again, suffer from drastic performance issues. So in order to address this, I'll present our work in a system called Sandook, which unleashes the potential of data center SSDs by taming performance variability. And we do this through two key design ideas. The first one being routing flexibility, and the second one being timescale separation. So what do I mean by routing flexibility? Recall that in our disaggregated storage setting, if one of the SSDs, let's say, starts going and does garbage collection, it effectively means that the load that the SSD can effectively handle is much, much lower. And so you want to do something about that. And so if you have multiple choices to read and write from at any given moment in time, then you can effectively route around these congested SSDs, and to make sure that you can sort of back off some of the load so that these SSDs can recover very quickly. So we do this by two design ideas. So one is log structured placement for writes, which means that you can append your writes to any of the SSDs that are valid at that moment in time without having to route to any particular ones. So this gives you flexibility to reroute your write requests. And data centers already have replication for fault tolerance, so we leverage that, and we sort of also route read requests to the most appropriate SSDs at runtime. So a combination of this allows you to run diverse policies to address sources of performance variability, which we'll see in a minute. The other key idea is separating the timescales at which you take sort of routing decisions. So recall that these SSD characteristics may shift gradually over time. And the load that they're supposed to serve might also shift gradually over time at other timescales. So if you had a centralized controller that was making globally optimal routing decisions, it would be able to do so, but a bit slower. And sort of you cannot react to all of the other events that we saw earlier. So for example, these sub-millisecond scale events that happen like garbage collection need much faster reaction times, and you want to be able to immediately react to these without having to wait for the controller. So you want the controller for the slow path, but you want short-term detection as well through a faster path. And for that, we have a centralized controller for global scheduling decisions that are close to optimal and that evolve slowly by looking at the SSD profiles and assigning routing sort of policies to them, rules to them. And then you have clients that might temporarily disobey these rules in order to immediately respond to congestion signals that the SSDs give them. And so this allows you to do fast reaction times while maintaining close to optimal routing decisions over time. So as a result of these two ideas, I'll present what Sandook's sort of system design looks like. So on the left, you have compute servers. So you have your standard applications, which can talk to Sandook over a standard Linux block device. So for example, over /dev/Sandook, or through a file system, which internally, the block device talks to the rest of the system using a thin Sandook client. And you can have multiple compute servers. On the right side, you have storage servers, each of which has an SSD agent, which is responsible for the SSDs housed in that particular server. And you have a controller that sort of bridges these two sides. So it takes metrics from the storage server about the SSDs, and it takes metrics from the client about the system load. And based on this, it periodically updates scheduling decisions back into each of the storage Sandook clients. And so that's your control path. But recall that you also have a faster control path, which responds to fast congestion signals, piggybacked on requests directly from the agent to the Sandook client without the controller involvement. So a combination of this allows you to handle variability at different timescales. On the data path, you have routing flexibility because the controller has already informed the clients of the most up-to-date scheduling decisions, so where you should do your writes to, and so you replicate your writes to the most appropriate SSDs without involving the controller in the data path. And you can read from any of these SSDs based on the replicas that you've written. So all of this together allows us to implement policies to address performance variability. And let's see how we can do that. So you have performance variability that we saw, so the first one being device heterogeneity. And in order to address that, we have profile-driven load steering, which says, don't treat all your SSDs the same, consider their profiles, and steer load according to that. And the design aspect that allows us to do that is that we have SSD metrics and system load at all times. Next, we had read-write interference. And we have a policy that physically separates reads and write operations onto a different set of SSDs because we have routing flexibility and we have replicas and choices to route our requests to. And finally, for garbage collection, we have storage congestion control, very much inspired by TCP-style congestion control, which reacts to congestion signals on a faster timescale. So in the interest of time, I'll talk about the first two, but I invite you to refer to our paper for more details on all the policies. So for profile-driven load steering, we want to incorporate the performance profile of each of these SSDs to satisfy two objectives. We want to satisfy the overall system demand, and we want to minimize the latency of the overall system. And we do this using a linear program. Again, details are in the paper. But we'll consider a small example to illustrate the point. So on the left, you have sort of a black SSD and a gray SSD on the right. The left one has a performance profile that peaks at around 1 million IOPS under the latency SLO. The right one peaks at around 0.7 million IOPS. Now, if at any moment in time, the total demand that I have to satisfy, let's say, is around 1.6 million IOPS, and if I were to do it using, say, most existing systems that overlook these differences, then I would naively just offer half the load to each of these SSDs. Now, notice how the SSD on the right is already beyond saturation and is violating SLOs, while the SSD on the left already has underutilized IOPS that we could have tapped into. So we're in the worst of all worlds. We're not using our precious resources properly, but we're also violating SLOs. So using Sandook, you can actually assign appropriate weights based on these profiles, such that, for example, in this case, you can route about 60% of your reads, your operations to the left one, about 40% to the right one, and you're able to sort of maximize the utilization of your resources while also satisfying the load and keeping your latency SLOs met. The other policy that we implement is read-write segregation, which allows us to physically separate these two operations to minimize mixing of the two. And so we assign modes to these SSDs, which can either be in a read-only mode or a write mode. And we want to minimize the two operations landing on the same flash media. So if you don't do this, let's say you'll mix the read and write operations on all the SSDs, you'll, let's say, have 0.4 million IOPS that each of these SSDs can deliver. And that's suboptimal, as we saw earlier from the characteristics. But if the controller is able to segregate these SSDs and tell the clients to only route the write requests to the rightmost SSD and the read requests to the left two SSDs, then each of them can deliver much higher IOPS, an aggregate of 2.2 million in this example compared to the 1.2 if you were mixing these. And nothing has to change on the SSD side. It's just the controller informing scheduling decisions to the client so that they can appropriately route their requests to the most suitable SSD at that moment in time. But we also want to switch these modes rapidly so that new blocks can sort of be written evenly across the SSDs, so the controller will periodically update the routing modes, and the clients will obey the new modes when the policy is updated. So let's see what this buys us in terms of performance. Now, recall that we have throughput or IOPS as million as the metric of interest for now. A static routing policy, as we saw, is only able to achieve about half of the ideal theoretical throughput that we are able to sustain. So systems that overlook all these variability will only get you so far. Then if you start looking at only congestion signals, and which some of the prior work does, then you're only able to manage your tail latency, but you don't get much improvement in throughput. If you're only physically separating reads and writes, but overlooking other sources of variability, that only gets you so far, about 3 million IOPS, still far from ideal. And then weighted routing gets you a little bit closer, close to 4 million IOPS. So the key point is that individually catering to any of these policies, which a lot of prior work does, is not sufficient to tapping all of the potential that the SSDs have. And so Sandook's holistic approach unlocks 95% of the ideal throughput by combining all of these policies, which our design allows you to do. In other words, under the same dollar cost budget, you're able to deliver about twice the throughput. And as we saw, SSDs are pretty expensive, so you want to be careful how you use them. So in conclusion, I've shown you how Sandook can unlock high performance and high utilization of a shared pool of SSDs while running co-located workloads of various characteristics. It manages various sources of performance variability in the data center SSDs through two key ideas of routing flexibility and timescale separation. In our evaluation, we're able to see about 1.7x higher storage throughput compared to existing systems, 1.9x application level throughput improvement, and about 88% lower latency. And this is with co-located real-world unmodified applications running on a shared pool of SSDs. It is Linux compatible without requiring any application code changes, so you can run different file systems or directly use a block device to access Sandook. And it's available as open source software at the following link. I'm happy to take questions now. Thank you.